All right, so I thought we'd just start with a quote. I've been reading a book about evolutionary psychology at the moment, and I thought I'd share this with you. It's just talking about the theory that art and culture are byproducts of our survival adapted brain, but the author says that this idea fails to explain why it is so much harder for us to learn mathematics than music, surgery than sports, and rational science than religious myth. The author's sort of overall point is that our brains are actually adapted as like courtship machines to help us reproduce and survive. But I think I like the quote about mathematics because, our brains, it certainly feels to me as though they're not adapted to think in the ways that we're sort of making it think. So if it is difficult, these ideas for you, then you're not alone. So what we're going to talk about today is confidence intervals, and I think it's notoriously a difficult topic to wrap our head around. So I'll just start with sort of framing it as a problem, just so we can get a sense of the kinds of problems that we're trying to solve. So imagine we wanted to know the population mean, so that just means the average of IQ scores of all Year 12 maths students in Australia. Measuring the entire population is obviously not realistic. We can't actually do that. So instead, what we could do is take a random sample and use it to estimate the population mean, which has this Greek letter mu, right? That's what that symbol means, referring to the population mean. So for example, we could take 100 students and we could work out the mean of that sample. And then our question is, what can we say about the population mean? So, I've got some population, we're going to take a sample, we're going to calculate the mean of that sample. And then hopefully, if we've taken an unbiased sample, randomly selected, then this sample mean of 108.6, shouldn't be too far off the actual mean. So that idea there is what's called a point estimate. So let's just talk about these two ideas, and then we'll bring it all in together, what we mean by confidence intervals. So there's two kinds of intervals. There's two kinds of estimates we can talk about, and I'll just let this play for a second. The first kind of estimate is what's called a point estimate. So this is like the sample mean. So that number of 108.6 is what's called is obviously a single value, and that's our estimate of the population mean. It's simple, but it gives us no indication of how far off we might be. We don't know if it's exactly that or what sort of range we're in. So in which case we're going to use what's called an interval estimate, also known as a confidence interval. So this actually gives us a range of plausible values for the population average. And a 95% confidence interval says, and this is where it's tricky, it says if we repeated this sampling process many times, 95% of the intervals produced would contain the true population mean. And now I'm going to go over this point a million times because it's really subtle, statistically heavy language. So we'll go over this point a few times as we go through. But if we just look at this diagram here, we can just get a sense of what we're sort of saying. In the point estimate here in blue, we've got 108.6. That's just from one sample. The population mean is actually unknown. We never know that, right? We don't have access to that. We can't actually do a survey of every single Year 12 student. So this will always be unknown. The population mean is always going to be unknown. In this case, it's a little bit larger than 108.6. But we can construct what's called a 95% confidence interval. And so we can say, and I'll explain where these numbers come from in a moment, but we could say we can construct an interval estimate or a confidence interval of 105.66 to 111.54. And this is, what's called an interval estimate. And so, I don't want to, the thing I want to say right now is that there's a 95% chance that the population mean is in that interval, but that is not what it means. So I'm very cautious not to misspeak because it's a very subtle point about the confidence intervals. I think as we go through an example, it will make sense. There's one particular diagram I'm keen to show you that will explain things. Let's talk about how we're getting to these sorts of conclusions at all. And the foundation of being able to set up a confidence interval is a strong understanding of the central limit theorem. Now, I'll put a link below for my previous video where we spoke about the central limit theorem. Big picture stuff here is that no matter what the distribution, when you start sampling your population, it's going to be a normal distribution as long as you take enough samples, essentially. So even if you have a heavily skewed piece of data, if you start taking samples out of that population, the distribution of the sample means, or the distribution of the means of the samples, will be normally distributed. And we spoke about these two facts before. The expected value of the distribution of the sample mean is just what we're going to call mu, and the standard deviation is sigma on the square root of n, which is the standard deviation on the square root of n, regardless of the shape of the original population. And that's the big takeaway of the central limit theorem. But definitely go and watch that other video. If you're unsure about this idea, because it's fundamental to this idea of confidence intervals. Now, we all know, hopefully by now, that the normal distribution looks like this graph here. You know, it's centered on the mean here, which is mu. And we got to talk now just a little bit about standardization. So we can see here that 95% of the data, shall we say, is between negative 1.96 and positive 1.96, where Z represents a standardized normal distribution. So we're going to talk a little bit about standardizing, because, you know, in the real world, you've got sets of data that have means and standard deviations, you know, that can be whatever. And, you know, to standardize it is to make the mean 0 and the standard deviations equal to 1. And so that's what this sort of graph here is showing. But let's just talk about that standardization process a little bit, which is also called a z-score. I'm just going to pause so I can, you know, really explain it well, because I don't want to miss anything important. All right, so let's just step through this idea of the z-score. So the central limit theorem tells us that the distribution of the sample mean is approximately normal with a mean of mu and a standard deviation of sigma on the square root of n, which is what we spoke about. All right, to use standard normal tables, we standardize it using this general rule. So Z, your Z-score, we can call it, is equal to the value minus the mean over the standard deviation. Let's just pause on that first line there for a second. So let's think about, again, the height of women's heights. Let's say the average is 165, and then you randomly select someone for the population. Maybe they're 170 centimeters tall. So it's 170 would be the value minus the mean, which is 165. And then you divide by the spread, or how spread out is that distribution. And then that gives you what's called a z-score for that individual person. That person, in our example, because they're a bit taller than average, will have a positive z-score. And so that sort of standardizes it and then allows us to put it onto this standard normal distribution, which we have here. Okay? And I'll just point out that for the standard normal distribution, again, the mean is 0 and the standard deviation is 1. You literally, that's the definition of standardizing it. Okay, so we know from the previous, section that for normal distributions, I should say this carefully, for the distribution of the sample mean, the mean is mu and the standard deviation is sigma on the square root of n. So if we just plug those into here, we plug in the mean mu and we plug in the standard deviation, which is this, we know that for approximately normal distributions that the z-score is standardized in this way. So we get a z-score for x bar being, this thing, this annoyingly looks confusing fraction, but this is what all the terms mean in this blue box here. And we know that, obviously z follows a standard normal distribution. Okay, hopefully that's making a bit of sense. That's the idea of sort of standardizing, which probably should be its own video, but hopefully you've come across that idea as well. And so for, again, just to really drive it home, so z equal, the mean of our standard normal distribution is 0, and that corresponds on the original sample mean distribution of being an average of mu, which we've called mu. Okay, so hold that stuff all in your mind all at once, if that's not hard enough. And so now we can derive a confidence interval. And this, I'm just going to let this play, but, the maths is what it is, but we'll talk about what it means. So we standardize our distribution, and we can say that, and this is just a feature of the standard normal distribution, the probability of 95% of containing 95% of the data is between negative 1.96 standard deviations and positive 1.96 standard deviations. And so we can start to decide on our 95% confidence interval. Essentially, we know that the right-hand side has to be equal to 0.95. Essentially, we're integrating the area between 2 points to be equal to 0.95. Because we know that we're talking about a probability density function here. So we need the area underneath the entire thing to be equal to 1 because everything is contained underneath the curve, right? And so essentially, if you were, thinking, pictorially, we need 95% of the data to be in the middle. It turns out that, yep, this is what you need to do. And then, you just rearrange these inequalities like you would rearrange equations. And so you end up with this. I'm going to try and read it, but hopefully you can just have a look. So the probability that the mean, so 95%, there's a 95% chance that the mean of your distribution will be between x bar minus 1.96 multiplied by sigma on the square root of n and x bar plus 1.96 multiplied by sigma on the square root of n. Okay, these two terms, once we've multiplied them accordingly to the other sides, is what's called the margin of error. Okay, so our 95% confidence interval is given here in blue. This is how we compute a 95% confidence interval. Okay, big picture stuff. Let's, think about what this really means. And I've actually, been thinking about this quite a bit. So I really don't want to get it wrong. I've recorded this video before, but I said things incorrect, so we're doing it all again for fun. So let's have a look at an example here and see if we can work through it. So we always know, well, let's look at a worked example. So we don't know the standard deviation of the population, just like we don't know the mean of the population. This is why we're taking samples, right? But in this problem, we're going to say that the standard deviation is being given to us. Okay, so we're going to say that the standard deviation is 15. And, for IQ tests, that's actually known. That's a known thing about IQ tests. The standard deviation is 15. The sample we took of our Year 12 students is 100. The sample mean we got was 108.6. And we want a confidence level of 95%. So the confidence level of 95% gives us these 1.96 values. Okay, this is something that would be on the formula sheet, for example. And so we can compute a margin of error around that point estimate that we got for the mean of our sample, right? So it turns out that the margin of error is 2.94. So to get the lower bound of our confidence interval, we get 108.6 minus 2.94, which is 105.66. And then the upper bound is 111.54, and we get that by just adding 2.94. Okay? And yeah, this is our result. So we are 95% confident that the true mean lies in this interval. Okay, lies somewhere in that interval. And now saying 95% confident is not the same as saying there's 95% chance. Remember, the mean, we don't know it, but it's either in that interval or it isn't. So it has a probability of 100% or 0%. But to say that we're 95% confident is making a very specific statistical claim, which we're just going to talk about here. And it's this. I'm just going to move my head 1 second. All right, so we're just going to presume that we somehow, magically knew the population mean, and it turns out to be 110. And so we pretend to know it to illustrate sort of this concept. In reality, we never know it. But repeating the sampling 20 times, what we're saying is 19 out of 20 times, which is approximately 95% of the time, the confidence interval should capture the population mean. Okay, I want to just even say it one more time because it's a very important point. So that interval that we captured before, now I can't remember what it was, but I think it was like, let me check. It was 105.66 to 111-ish. So say 106 to 111. What's been tricky for me personally to get my head around this idea is that's actually not unique. That's just one interval estimate we made using this methodology. And what it means to say that we're 95% confident that the mean sits within that interval estimate really is saying we have trust in the process that 19 out of 20 times, or 95 out of 100 times, the interval will capture the true population mean. And so, I'll just, I think, I don't know, hopefully that clarifies it. This diagram, I think, says a lot as well. So we're just sort of invoking this idea that we have trust in the methodology. And yeah, we can see that, there's 20 interval estimates here. One of them misses. Obviously, we don't know that this one misses in reality because we don't know what the true population mean is. But I heard a good analogy as well. It was like, you're using it's like you're going fishing. You're trying to find the population mean. You're using a large net. The net that we used, in the IQ example for year 12 was 106 to 111, and we're 95% confident that we've captured the population mean in that net. But we could have used a different net, and we might have missed it. But that's the risk we take, and that's a very subtle but important point. All right, too much talking, so let's keep trucking. Let me move my face again. All right, so here's our summary. Hopefully sort of getting the big picture, just a few points. So the central limit theorem guarantees that the distribution of the sample mean is approximately normal for large enough n. We standardize using our standard normal distribution, 1.96 either side, standard deviations either side of the mean, guarantees a 95% confidence interval. So I encourage you to think about how those values might change if you needed a 99% confidence interval. In practice, the standard deviation and the standard deviation of the population and the mean of the population are unknown. But when you don't know the standard deviation of the population, you can use the standard deviation of the sample as an indicator of the population's standard deviation. And the 95% confidence means that the method, and that's the key part, captures mu in 95% of repeated samples. It is not a probability statement about that one interval. So technical, important points, all good stuff. Hopefully that's making a bit of sense. If you find these videos useful, give us a thumbs up. Keen to hear what you think, how it's all going. Statistics is, very different to the other stuff you do, but hopefully you're finding it fascinating. So good luck, and I'll talk to you soon.